Hello, this is Chengxi from Purdue University. In this video, I'm going to present my paper about risk object identification via causal inference. This paper was done when I was an intern at Honda Research Institute and collaborated with Stanley Chen and Yiting Chen. The motivation of this work is to improve the driving safety. As we know, car accidents happen every day, and the number of fatalities is horrible. According to Global Status Report on Road Safety in 2018, there are more than 1.3 million people dying in road accidents worldwide every year, and up to 80% of these accidents are due to driver inattention in dangerous situations. This has motivated researchers to develop new intelligent driving systems, assisting drivers to identify potential risks. The identification of potential risks have been studied extensively in the risk assessment literature. Most of them defines the risks based on collision predictions, but collision is not the only source of potential hazards in driving. For example, unexpected objects or events such as debris or construction areas are frequently encountered. They don't necessarily result in collisions, but are also considered to be dangerous. Based on this, we propose a new definition of risk, which is objects influencing drivers' behavior are risky. Imagine driving in a scenario on the right, that we are planning to pass the intersection while yielding to a crossing pedestrian. If the pedestrian does not exist, for example, we remove it, the ego car could have passed the intersection without stopping. In other words, if we did not slow down or stop, a dangerous situation would occur. Compared to previous definitions of risk assessment based on collision predictions, these reactive scenarios are more commonly encountered than collisions. Therefore, we believe that the proposed definition captures various learning signals for assessing risks. Then a nature question arises: who makes drivers stop? We propose a new task called risk object identification, which aims to identify the object influencing drivers' behavior. The proposed task can be approached via two existing methodologies: supervised learning-based algorithms and attention mechanism-based method. First, supervised learning-based algorithms are trained to regress risk object's location or to generate a driver attention map using human gaze as supervision. Specifically, for the first one, the risk object identification task is formulated as an object detection problem. Alternatively, for the second one, the task can be treated as pixel-level driver attention prediction by mimicking human gaze behavior. However, labeling risk objects using bounding boxes and human gaze behavior is noisy and time-consuming. Another method is trying to select regions or objects with a high attention heat learned from an end-to-end driving model with an attention mechanism. The output of the driving model is a prediction of driver behavior. The attention could be pixel level or object level, but these approaches do not explicitly reason for identifying risk objects and leads to causal misidentification problem. Our proposed methods are different from existing ones, in that it is weakly supervised, requiring minimal annotations, and it has a causal reasoning process. We formulate our task as a causal effect problem using structural causal model. We do not discuss the details of structural causal model in this video. We discuss how we implement this idea in the risk object identification context. The core idea is simple. If we apply some intervention on the cause, it will result in the change of effect. To be more specific, here is our pipeline. Given visual input, a driving model is learned to discriminate whether the ego car should stop or go, and then we apply some intervention to the raw input by iteratively removing objects from the image. Due to the special design of our driving model, it is able to simulate a situation without the object and predict the ego behavior as if the object does not exist. If we notice the ego's behavior changes from stop to go, then we can say that the removed object is a risk object. To get reliable identification results, we need to design a robust driving model, which is manipulable at an object level and is capable of imagining what the scene looks like without the existence of a certain object. Let me give you a more detailed picture of the driving model. Basically, we have two branches to process the visual information. A sequence of video frames and corresponding masks will be input to partial convolutional layers in order to obtain a global feature. Partial convolution operation is first introduced in the image inpainting application. This special design enables the hallucination in the masked area. We can specify which area we want to remove pixel-wise by feeding a mask with the region masked out. Meanwhile, objects are detected and tracked to form multiple tracklets. We use ROI align to extract object features. These features are further used to pass information to ego feature and then form a final representation. We use this representation to predict whether the ego car should go or stop. Our special design of the driving model allows us to intervene on inputs directly. For example, if we want to remove this green car here, we can do the following. Pixel-wise, we can input the image by masking out the selected region. At an object level, we can remove the object node in the message passing stage. Then the selected object information will not be used in the final representation, so the system can make predictions as if the object does not exist. For training, we cluster and label the training samples into two categories. The first is go, where the ego vehicle moves without stop. Another is stop, where the ego vehicle stops or yields for something. This is the only supervision signal that we use in the training stage. We do not need to use the bounding box's information during training. It is weakly supervised. As we know, driving model can be improved by training on samples with different traffic configurations, but due to the limited real-world human driver demonstrations, we do not have the access to that. So we design a training strategy and borrow the concept of intervention from causal inference studies to improve the robustness of the driving model. We generate new configurations by following a simple logic that the removal of non-causal object does not affect the behavior of the ego vehicle. For example, in the go scenario, the ego vehicle goes straight and passes an intersection. Removing any pedestrian walking on the sidewalk will not influence the behavior of the ego vehicle. So when we train our driving model for those go samples, we are assured to remove any objects by the intervention strategy we just mentioned, and this won't affect the ground truth of the prediction. By doing this, we can bring more variations to the traffic configurations, making our model more robust. We evaluate the proposed framework on the HDD dataset and test it in 4 scenarios. There are yielding crossing vehicle, yielding crossing pedestrian, deviate for parked car, and stop for stopped vehicle. In terms of evaluation matrix, we report accuracy, which is the number of correct prediction over the number of samples. A correct prediction is defined to have an IOU score between the selected box and the ground truth box above a threshold. We set the threshold to have different values, such as 0.5, 0.75. We also compute a mean accuracy, which is computed by averaging accuracies at 10 different IOU thresholds, evenly distributed from 0.5 to 0.95. In terms of quantitative results, our approach achieves the best performance. The first method randomly selects one object as the risk object from all the detections for a given frame. This method does not process any visual information, and we show the results here to provide a basic measure of the difficulty of this task. The second one is a supervised learning-based method. The model is trained with human gaze information, which is unavailable in the HDD dataset. Therefore, we use the model pre-trained on the BDDA dataset. The performance of the method is slightly better than random selection. By visualizing the predicted attention map, we discovered that the heated spots tend to cluster around the vanishing point, and this is one of the challenges of imitating human gaze behavior. The third one and fourth one are both attention mechanism-based methods. Specifically, the fourth method's performance is the closest to our results, since the causality test is similar to our inference with intervention. Our performance is better because our driving model is manipulated at the object level, and it is trained with the intervention strategy for robustness. Here is our visualized results of risk object identification. And more qualitative results. In addition to select only one risk object, our framework can also be applied to assess the risk of every object in the scene. The eagle vehicles in the examples are supposed to take a stop action. All detected objects are encased in bounding boxes with different colors, and their risk scores are in a bar chart with corresponding color. The risk score of an object is equivalent to the predicted confidence score of go action after removing it. A higher score of go action means a higher possibility that it is the object that stops the eagle vehicle. We use a black horizontal line to indicate the predicted confidence score of go action when the input is not intervened. If the score is less than 0.5, then the sample is classified as stop. As we see in the figures, our framework can assess risks of each object effectively. An interesting example is noticed here. When multiple risk objects exist, say a group of people, our framework assigns high risk scores to all pedestrians. The result seems correct at first glance. However, even if one of the pedestrians was not present, the eagle vehicle should have stopped. Our conjecture is that the partial convolutional operation not only hallucinates the removed area, but also affects the surrounding regions due to the growing receptive field as networks go deeper. As pedestrians are adjacent, removing one person by partial convolutions may dilute the surrounding ones and return high-risk scores. To verify the conjecture, we manually inpaint the image by masking every pedestrian iteratively and feed the inpainted image to the same driving model without applying partial convolutions. And here are the corresponding results. A lower risk score of each pedestrian is observed that aligns with our intuition. It also proves our conjecture that partial convolutional operations influence the behavior of the proposed driving model, while more studies are needed. To summarize, we have three contributions. First, we introduce a novel driver-centric definition of risk and a new task called risk object identification. Second, we propose a novel two-stage risk object identification framework based on causal inference with a proposed object-level manipulable driving model. In the end, we demonstrate favorable performance on risk object identification in comparison with strong baselines on the HDD dataset. For future work, we think explicit intention modeling of driver and traffic participants will be beneficial. Additionally, a more sophisticated driver behavior modeling that considers acceleration, brake, and steering angle are essential for reasoning on the cause and effect. Furthermore, it will be valuable for practical applications to formulate the framework into a single-stage framework. Thank you for watching this video.